Hello and welcome to today's video, where we'll be talking about lock-free programming. We're going to start, of course, we'll be using C programming language. We're going to start from first principles, from a single atomic load, basically, all the way to identity folded compare and swap. This is a pattern that most production runtime uses, but in my opinion, not enough textbook covers. This area of programming is very, very specific. We're kind of diving into the deep, dark corners of programming, if you will. We're going very low level. We're going to have to dive deeper into how the CPU operates. In general, the CPU structures. We're going to also mind or understand how different CPUs operate. How, for example, ARM CPUs differ from x86, that is Intel, AMD architectures. And this is all about creating efficient and performant and extremely fast, that's our end goal, is speed concurrent programs. I'm planning this series to contain 5 videos. Today's video is part 0, which is the prologue. It is for anyone who has not written threaded C before. I would suggest that you still get more experience in C if you're watching, if through this video you feel like you're not comfortable enough, and come back later. But we're still going to cover threads. We're going to kind of explain p-threads, how threads work, races, mutexes, atomics. And so if that sounds like you, feel free to start here. If you already know all of these, you can skip this video. Before we begin, let's kind of walk over the checklist, if you should skip this video or not. So is this part for you? Well, if you're already familiar with all of the following points, then you can skip to the next video, if it is uploaded, that is. But if you don't know what a thread is and how it compares to a process, or if you don't know why kind of modifying the same variable in 2 parallel threads is a bad idea, or you haven't used pthread mutex lock, for example, or you don't know what it does, if you've never used atomics, or you're unfamiliar with the concept of atomics in general, or you don't know what compare exchange does, then I think it's a good idea to stick. If you know some concepts, feel free to jump around the video and just kind of learn the concepts that are new. All right, let's start by addressing the elephant in the room, the thread. More importantly, what separates a thread from its nemesis, if you will, a process? What is the difference between the two of them? Well, simply put, a thread belongs to a process, and the process can have many threads, right? It's more of a hierarchy, if you will. And the idea is very simple. If you have 2 running processes on your machine, and of course there is the operating system in the middle, it is kind of structuring or organizing how things run, etc., etc. And every process has its own kind of memory heap. And the idea that, for example, this would be process 1, this would be process 2. The idea is that every process has its own memory, for example, and so process 1 has access to the upper part, and process 2 has access to the lower part. So, for example, if process 2 tries to read memory that belongs to process 1, then the operating system will say, nope, segfault. So kills it, basically. It's like, why are you reading memory that doesn't belong to you, right? Because you could have keys, you could have like sensitive information, basically. And that's the idea, that every process have this kind of isolation of memory, but also a process has at least one thread, because at the end of the day, a CPU is going to execute threads. But let's talk about that in this slide. So we have the idea that a process is kind of this huge block that is isolated from the rest of processes. And within a process, you can have multiple threads, right? We have, for example, here thread 1, thread 2, and also we have a heap, and this heap belongs to the whole process. Hence, all the threads can access the same heap and the same global variables. However, every thread have their own registers and their own stack, and these are kind of local to the thread. And why is that? Well, because when you're running multiple threads, the CPU can execute one kind of vCPU, can execute only one thread at a time. And so you could have like 4 vCPUs, or you could have like 16, depending how good your machine is. But at one given time, so if I have like 4 cores, each of these cores will be running only one thread. So this could be running thread 1, this could be running thread 5, thread 7, and not thread 0. But a core, it can stop executing this thread. And for example, we have thread 10 waiting. It needs, when it wants to stop executing this thread, it needs to back up its registers, the instruction pointer, the stack, basically, and everything. And so all of that data is private to a thread, so that if the core wants to resume it later, it knows from where to continue in the program, right? So there is the idea of thread and a process. And a few important things is that 2 threads in the same process can both write to the same global variables. And it's the fact that they can both write is why we're doing this series, basically. And so if they both can read, then kind of it's perfectly fine, right? It's like 2 people can read the same page, if you will, but if they start to write on the same page at the same time, then it would be chaos, which is what we're going to see exactly in the next few slides. So to start off, if you've never written a threaded program before, here is pthreads basically in 5 calls. The idea is that we have our the function that we want to execute in parallel, right? We want to say hello from thread 1 and 2. So that is the function. It's going to be, we want to spawn a thread. I think that's the proper terminology, is to spawn a thread. And it's just going to print that and kind of return nothing. So we pre-allocate our variables. So we prepare thread 1 and thread 2, they're pthread t. A and B equals 1 and 2 respectively. These are our IDs, and then we just call pthread create. So T1 is going to host our first thread. The callback function is worker, and A is essentially the argument. It's the ID that we want to pass. And because this is C program, it's not type safe in the sense that you have to kind of cast it, or argument passing is done via like a void pointer. And so you kind of need to know how you sent it, and so that you can know how to decode it. Usually it's the other way around. You need to know what you need within the worker, so you kind of encode it properly, or send it properly from the thread create. So we are doing the same thing for thread number 2. And then we have thread join T1, thread join T2. And after this line, so we have a new thread that's running. And after the next pthread create, we're going to have another thread that's running. And the idea is that before our main exits, we want to wait for the thread to finish. So the first line is going to block the main, and it's not going to execute any instruction after until until thread 1 finishes. And then we wait for thread 2. So it doesn't matter if you swap the order. Like what matters is the outcome, that we do not go further until all the threads. It's kind of a cleanup mechanism, right? You don't return, because main is kind of the parent thread, if you will. If we look at this from a timeline perspective, I'm going to model the main in yellow. This would be our main. And then at some point we are spawning thread 1. And at another point we are spawning thread 2. Now what's important to understand is that we don't really have control over which thread runs first. You kind of can if you spawn thread 1 and then wait for it, and then spawn thread 2. But if you spawn them like pthread create T1 and then pthread create T2, the way or when they're executed is dictated by the operating system, by the scheduler of the kernel, and we do not have control over that. So that's non-deterministic, and that's something that we have to live with, essentially. And so what pthread join does is that it will tell the current active thread, which right now we're in main. It will ask main to hold until this thread finishes. And then we have another hold until this one finishes. So actually T2 could have finished earlier, right? But we're still kind of waiting for T here. So we're kind of making sure that main stops until this thread is finished. And so what I'm trying to say at this point is that just because we spawned, so first of all, our two threads are running the same function, which is worker, but just because we spawned T1 first doesn't mean, or doesn't necessarily mean that it will be the one that finishes first. So the operating system could actually prioritize T2, thread number 2, and thread number 2 will finish first. And yeah. Next, we want to talk about the race condition. There are two technical important terms here. The first one is race, which indicates, well, in our case, it's going to be two threads. And condition is usually a resource, like some variable X. And both threads are kind of competing over that resource, hence the whole concept of race conditions. So let's take an example where we have a global variable, counter equals 0. And then in our worker, the function that will execute in parallel, and in this case, it's going to be executed 10 times in parallel, so we're spawning 10 threads. We're going to iterate 100,000 times, and we're going to increment counter, right? So counter plus plus. Running this program, we actually expect 1 million. However, if we actually execute it, we're going to get very inconsistent results. And there is a reason for that. And basically the whole video is about how to overcome this problem, and not just overcome it, but overcome it as fast in a way that's really fast and efficient. However, notice that all of the values that we have are, first of all, random somehow, and they're all below the target value that we expect. And also this is the problem that we have to deal with, that in every run, we do not really have control over the order of threads. As in, yes, we can control when to spawn them. We can make them sleep given certain condition, but once they're all running, it's up to the kernel to organize when each thread runs. And that leads to some undeterministic behavior, and we have to deal with that. This is what it's all about. And so basically no two runs are identical. So you can keep running this different times and you're going to get always a different value. So let's first explore why are we getting this behavior? Why are we not getting our expected value? And this is, well, the problem is the race. That's like they're both racing to access the counter, essentially. And the whole problem is that counter plus plus is actually equals to simplify it, I plus plus is equivalent to I equals I plus 1. And there is actually three instructions. And so in assembly, it would translate to basically a load from memory, a modification, we need to add 1, and then a move back into the memory. And because we don't really control when each thread runs, it's controlled by the kernel. We could have, for example, the value in memory is being 5. And so we could have a thread here reading 5, right? And then adding 1. And then by the time this thread, for example, at this point, the operating system could put this to pause. And then we have another thread that is loading the value 5 that will perform the addition 6, and then it will store 6 into the new value, right? And then the operating system decides, like, this blue thread will now pause and our purple thread will continue, and the purple thread will now move also 6, because that's when it loaded the counter at first it was 5, and so it will put 6 again. And so we kind of lost an increment. And this is the idea that it's happening, the kernel is switching between threads, and each thread is like reading a value that is outdated, and hence it's going to move later on a value that is outdated. And that's why we're always going to get the value that is below our target. Of course, there is a solution, a well-known solution, which is a mutex. And a mutex acts basically as a lock. But let's first review how it is done in code. So first we have to define a mutex. Let's m is our mutex variable. And then in our worker function that will be executed in parallel, we first need to define the critical section, which is our increment. So the idea, we want this counter plus plus to be executed only by one thread at a given time. So in this entire section, basically anything between the mutex lock and mutex unlock, only one thread can access that. And you can think of it as like a token or a key, where the very first thread that gets into this function will acquire the key or the lock, and then it will get to increment. And before it releases the lock, another thread comes in and says, can I get the lock? And the operating system basically will say, nope, sorry, another thread is busy. And so it will basically go to sleep until the other thread releases the lock. Then the red thread can acquire it and continue. And the idea here is that you are going to have one kind of lock, and let me see if I can draw a key in here. Whoop. That's a really bad key. So basically you have one key and you have multiple threads wanting access. And the operating system is going to kind of, you take the lock and all the other threads are going to put to sleep basically. And when the thread with the lock releases it, we have unlock, then it's going to choose which thread to give the key to and wake that thread up. And this is important. The threads that are kind of waiting for the lock, they are parked. So asleep, which means they're not really wasting CPU resources. And in a more or less a normal project, you would usually use more than one lock. If you have a lot of data structure, if you have a lot of things to synchronize, then you would end up using more than one lock. And it so happens that there is a very kind of deadly case, which is called deadlock, where basically you have thread A that is holding lock 1. So it has lock 1, and it is waiting for lock B, or sorry, lock 2, right? So thread A, it holds lock 1 and it wants to acquire lock number 2. However, lock number 2 is actually being held by thread B, right? Who is currently waiting for lock number 1. And so it's a deadlock. They're basically stuck waiting. And yeah, this is where your program would run forever without actually doing anything meaningful. So it's just stuck, right? You just kill the process at this point. And so this is one of the common problems that you may encounter when dealing with mutexes. And I'm not saying that this is the problem that we're trying to solve. I think mutexes can be or are actually the answer to many problems, but you have to kind of reorganize or re-architect your problem or your program rather around locks so that you keep track of which thread holds which lock at a given time. And so the architecture of the program or the flow of the program needs to take locks into account, right? Otherwise it would just be a mess and you don't really know which thread is holding which lock, and eventually you're going to end up with one or many deadlocks. And this is what we're going to use as a baseline for basically our future work, which is atomic operations. Atomic operations are kind of a subset of operations that are indivisible, which means, for example, I++, we know that this is not atomic, it is 3 instructions. But what if we could model this? We had like a magic function that actually does this, but a thread would see it as a single instruction, meaning indivisible, like you cannot really divide it into sub-instructions from a thread's perspective, while also not being a system call. There is. And that's what we're going to talk about. That is actually the definition of an atomic operation. So this is the same increment problem. However, it is solved without a lock. Underscore atomic int basically declares the variable as atomic. So it means like since we have an kind of a set of functions that are atomic, they usually have to deal with atomic variables. So they go hand in hand. And in our case, we have our worker function, which is the exact same. Instead of counter plus plus with a lock in between, we are using atomic fetch add. It's as the name suggested, we're going to atomically fetch counter and add 1 to it. Right, so it's going to do the entire counter plus plus for us, except it can also work for like plus if you want to add 2, or if you want to subtract, etc. You can do a lot of things. What's important is that atomic functions require atomic arguments, at least the one that you're modifying, so that's why it's an address. Now, to avoid confusion in general, as I mentioned now, since counter is an atomic, it is actually going to kind of compile differently under the hood. So if you do printf, for example, right, %d, and then you specify counter, what's really going to happen is the compiler is not going to emit counter here. It's going to emit atomic fetch instead, which is a function that kind of gets the snapshot, if you will, of counter. So you can think of it as like as a meta type, right? You have counter, which is an integer, but now it's also atomic, and so it compiles differently. And that's why, even though we can access the variable directly, we are directly going to use atomic fetch because it's much easier to reason about. When you're reading, then you kind of know that this is an atomic variable and we need to use atomic fetch to get the latest value. It's slightly complicated, but let's look at an example and see how it works in practice. But the idea is that if we compile this program, we're going to get the exact same output no matter how many times you run it. So there are a lot of instructions such as atomic load, which in the previous slide I said atomic fetch, sorry, it's atomic load. And there is also atomic store. And we have atomic fetch add, which we just used. And there are a bunch of other functions that we're going to discover. Again, these are all C11 atomic API, essentially. The next thing we want to talk about is compare and swap. Compare and swap, again, let's reason a little bit about the name. So there is compare, so it's like a condition. Is something equals, bigger, smaller, etc. And swap. So the idea is that we're going to have a condition, and if that condition is satisfied, we're going to perform a swap. And yes, this is atomic. And understanding the compare and swap is key to understanding lock-free algorithms, because we're going to use this the whole time, essentially. So let's see how the signature, or the behavior rather, of this function. So compare and swap is a function that atomically updates an atomic variable based on a condition. And the idea is as follows. So atomic compare exchange, don't worry about strong. There's also weak. If you have strong, you have weak. And the idea, it requires 3 arguments. The atomic that we want to update. So here actually atomic atomic int counter is missing, but you get the idea. It needs to be, we need the address because we're going to mutate it. And we have an expected value and we have a desired value. Now, again, it's an atomic function, right? And it returns success if the counter was equal to expected, and it fails if counter is not equal to expected. And what it does instead is it mutates expected, we have an address here, with the real value. So let's have an example. We're going to look at two cases, one where we have a single thread and one we have two threads with kind of like an example. So case number one, we are going to have some slots here. This is our counter, this is our expected value, and this is our desired value. So we expect 10 and we desire 11. So let's be optimistic at first, and let's suppose we have initial value of 10. What atomic compare exchange is going to do, it's going to basically compare the two values. It's going to compare the expected with the desired, with the actual counter, and since they match, it's going to update the value of the counter to 14, and it's going to succeed. So basically it's going to enter the block, it's going to return true. However, let's have a sad case right now, and let's say it's equal to 15. It's going to compare. 10 is not equal to 15. So what it's going to do instead, it will set the expected value back to 15. And it's not going to update. But you will know that it didn't update because you will be in the else block. Why is this useful, or how is this useful? Let's look at another example. So this time we're going to have two threads running. And so I'm going to model it as follows. So this is our counter, expected and desired. And so our counter initially had 10, right? We expected it to be 10, and we want to set it to 11. Now, the problem is, let's suppose that the CPU halted my thread here. So I didn't get to perform. It's literally just before it executes this atomic exchange. Another thread comes in and sets the value of counter to 100. So now this value is no longer valid. And so what then my process or my thread is going to continue, and I finally get to compare the expected value against the counter. Are they equal? No. So what it's going to do instead, it's going to fail. So it's going to take me to the else block and also update the expected value to 100. So it's saying that, hey, I couldn't update because the condition is wrong. So the expected value is wrong. And it's going to mutate it to give me the new value instead. And that is the whole idea of compare and swap. Now, let's look at a practical example. Why would we need this? Here is a practical example. This is our increment. So basically, it's the same increment of a counter, except we're not really going to use fetch add. So we know we can use fetch add, right? It's a one-liner, but we're kind of addressing the problem using atomic swap instead, just to kind of understand why we need this. So in this case, we have our counter given as an argument. So we have our counter as an argument, and we're using load atomic. So we have atomic load counter to kind of get the latest value, right? And then we're preparing a new value. And what we're doing is we're going to loop, right? We have a do while. We're going to increment the new value with the old value. And then we're going to compare exchange week counter. Again, don't worry about this weak and strong. It's just to explain a little bit. It's a tiny bit difference. If you're on Intel CPU, it will basically compile to the same bytecode, but it has same instruction, but it has a slightly different behavior on ARM processors. And so it's because these kind of primitives, they have to be, portable, then it kind of, the standard, so to speak, has to take into account different hardware capabilities. But it will become more relevant later. For now, it's just compare exchange as far as we're concerned. The idea is that initially, and I'm going to draw the same table. Let's take the happy path first. So we have our counter, we have the old value, and we have the new value, right? So we're going to enter the loop, but first let's suppose we have 14 in here, and then our program gets into the or our threads, the function starts executing in our thread, and so we enter old equals atomic load counter. So now old is equal to 14, and new value, so we just allocated it. And so what we're going to do is we're going to set a new value to 15, basically. And then we have atomic compare exchange weak. Let's see if it's going to work. So let's say we have one threaded program, nobody edited the counter, and so we're going to compare old with counter. Does 14 equals 14? Yes. In that case, we're going to set the value to 15, and this becomes 15 now. All right. Now, let's take another case, which is the more likely case when you're in a multi-thread environment. So initially, as you go into this instruction, counter is equals to 14, and then your instruction pointer moves to the next instruction. Old is set to 14, but your process, your thread stops here. Operating system does a thread switch, another thread comes in and sets counter to 140. So now, when my program resumes, I'm going to set the new value to old plus 1, and old is equal to 14, so it's going to be 15. And we're going to do the compare exchange. Does 14 equals to 140? Nope, it's going to fail, which means the loop is going to continue, go back from the beginning, because we have a not condition. So if we fail the update, we're going to resume. What's going to happen instead, the old, we have to pass an address, will now become 140. So when it fails, it's going to copy the actual value into the second parameter, which is the expected value. In a way, it says, hey, you expected 14, but the variable contains 140. Here's the updated value. Try again. And that's trying again is what we're going to do. And we're going to set new value to old plus 1. So it's going to be 141. And this time around, no one interrupted us. So we're going to go again into the compare exchange. Does 140 equals 140? Yes. So we're going to set the counter to 141 towards the end. And that is the idea. So first we have to read the value, atomic load. And then we have to compute a new value because we want to kind of modify the counter, but we want to modify it relatively to its old value, right? We want to increment it. So we compute a new value, which in our case, this variable. And then we perform a compare and swap. And if someone beat us, means if another thread has already updated the value before we get to do that, we try again. Except when we try again, we do get the latest value. And so this kind of shape of read, compute, compare, and swap retree is really the shape of every lock-free algorithm that we are going to come across. And compare and swap is really a fundamental algorithm, and I hope that this makes it clearer. All right, I wanted to do some kind of practical part where we go over the code a little bit and run. I don't recommend that you skip this. There is like some very cool realization, I would say. So let me just put them all side by side. And the first kind of code is just our data race, where we have counter equal counter plus 1 with no atomics, no locks. And if we build this and we run the race version, we have, for example, 46% loss, 77% loss. So there, yeah, every run is kind of unique. You're gonna get completely random numbers. And if we run the mutex version, which uses pthreads, right? We have we're using mutex lock and then lock in between our critical section. Then we do get the correct numbers. And finally, we have an atomic version that uses atomic fetch add. And let's run number 3 atomic, and we get our numbers. So everything, I would say, work as expected. What I would say is interesting is now that we have, well, that we're using atomics and we're not really using mutexes, which are actually system calls, right? Because the kernel will have to kind of wake the threads when data arrives, and we don't really have control over that. So we kind of have to communicate with the kernel to say, hey, start, a critical section here, start a lock here and unlock here. These are all system calls, and we don't like system calls. We want to reduce the number of system calls as low as possible. Again, sometimes unavoidable, but that's kind of the general idea. And so now that we have a program without system calls, because these primitives, these are not system calls, and so they're more like they're atomics. They're not system calls. And the idea is that if I now benchmark, and I'm using hyperfine for benchmark, I'm gonna do 3 warm-up rounds, which means it will execute the program 3 times without counting or measuring its time, because it needs to be read from the file system, and then kind of the first 3 runs are usually slow, and the next subsequent runs are kind of stable, and we want the stable ones. So that will be a 3 warm-up rounds, and we want to execute O2 mutex and O3 atomic. And what you notice, or what you see, is that mutex run 2 times faster than atomic. And you're wondering, what the hell? And I would say, welcome. This is why we're doing what we're doing. Just because we turned it atomic doesn't mean it's faster. And it doesn't mean we can't make it faster, but it just means that there is a lot going on. Something else is causing the time to be slower. Because notice at the system time of the mutex, we have roughly 70 milliseconds in system time that is communicating with the kernel, right? These are kind of blocking operations. Say, hey kernel, start lock mutex, hey kernel, unlock, whatever. And we have 2 milliseconds of system time here. So theoretically, this should be faster, but no, something else. And notice that it's something more on a CPU level. It's not on a kernel level, right? Because the kernel, the system time is really low. So there is something else here. And what basically this series is all about, it's figuring out these things. How can we do better than this? And so, yeah, reality is often disappointing, but that is usually the first reaction. We're going to discover quite some awesome things. And yeah, hopefully I got you curious enough to watch the rest of the series. So the important takeaway from this prologue is that threads and atomics are completely different. So threads, they are managed and synchronized by the kernel. So you can think of almost every pthread call as a system call. So for example, spawning a thread is a system call. Mutexes, such as lock and unlock, these are system calls. Atomics, on the other hand, they are CPU instructions. These are instructions that the CPU basically natively supports. And mutexes, as we have seen on our demo, are sometimes the answer. It kind of depends on the problem at hand. In general, kind of as a rule of thumb, or the motivation behind lock-free data structures and algorithm is that we do not like system calls. We have also seen in the demo how much time the lock version spends in the kernel. So why don't we like system calls? And in general, lock-free data structures, they attempt to avoid or minimize system calls as much as possible. And the reason for that is system calls are not free. When you're executing a system call, such as lock, for example, your program will halt execution. So the CPU is going to stop your program here and then switch into kernel space and starts executing what the lock is actually doing. So realistically, your program is halted until, the lock function executes. And of course, it's natural for it to halt, but there is also some context switching in between where the CPU has to switch into kernel space, into higher privilege kernel mode essentially. And that switching essentially, and also it has to switch page tables and it has to execute the kernel code and then wind back. And so that switching is expensive. So it is the switching plus whatever, the switching time plus whatever the kernel code is. The second thing is that your cache essentially and TLB get nuked. So what the cache is, it's the L1 and L2 cache layers that are between the CPU and the RAM. The CPU does store sort of frequently accessed data in the cache, but when you're going to switch to kernel space, that cache is essentially gone because now the CPU is executing the kernel code. And so the cache will kind of contain the kernel's cache in a sense, if the kernel code is in a sense expensive and has loops and such. The other thing is the TLB, which stands for translation, look aside buffer. And so what this buffer is, usually your program doesn't get direct access to the RAM. Usually we have the physical RAM and we also have virtual RAM or virtual, it's virtual addressing. So let's just call it virtual. And it's the operating system essentially gives you this virtual RAM. And so when your program addresses a variable or a memory region somewhere here, the operating system will need to map it into the physical address. And that mapping also has a cost, right? And the idea is that the CPU kind of contains a cache of the most frequently accessed virtual to physical kind of addresses. It's kind of a local map. You can think about it as like a local map from virtual to physical so that the lookup is faster. And so when you're switching to kernel space, again, this cache is also nuked. If you made it to this to the end of this video, I wanted to say congratulations. That was probably a lot of information. Hopefully you had a notepad and you got to make some notes. Otherwise, the video will always be available. If anything was unclear, I was a little bit too fast on some sections. If you think maybe I should make another video like about compare and swap in details, or if anything comes up, let me know. Otherwise, thank you for watching and I'll see you in the next video.